Cool. Well, thank you all for attending. Here we are. So a couple things to talk about before we get started with the lecture. So number one, really this is it. Number one, lab exercise 1. Okay. So officially the due date is the day of your lab session, but of course, we are aware that students often have trouble with the first time around using Access. So we are reasonably forgiving about the first lab exercise deadline. Okay, so do your best to get it in on time, finish it, whatever, but don't panic. You know, everybody knows that things sometimes go wrong the first week. However, there are things you can do to make things go less wrong for yourself. One of those is checking out this stuff on Blackboard. So I'm going to drop out of this, pick a lab section. Let's say Wednesday. I got a Wednesday one here. Okay. So all the stuff posted up on here on Blackboard, right? Lab exercises. There are two files along with the exercise. One of them is how to get Microsoft Access, right? It tells you if you can't get it in the lab, of course, you can use UIC's virtual desktop service, or there's other things you can do to get it. The second one is using Microsoft Access. And in particular, there's a bit here, I've already had to tell a couple of students that there's two kinds of access files. Number one is the ordinary file with the extension ACCDB, Access Database. Those are, ordinary access files. You can open them. The other kind that you can't is the extension LACCDB, or lock access database file. That's a file format that's used internally by Access, and nobody on the outside will be able to open it. So that's something there you should be aware of. So when you're uploading your work, upload the ordinary access file, not the lock file. There's some other things about here, common problems. You'll save yourself some time and misery by using those, right? By reading those documents. Let's see what I have here, getting MS Access. Oh yeah, and if you want, you can always just go to YouTube. There's a link I have. I listed it in one of the other sections that was remote because they definitely need it. But you can look on YouTube for older versions of the exercise. Let me score a copy of it here. I posted it with some of the Monday ones. I will post it eventually with the others. All right, so if people want to lab exercises, do I do it as an announcement? Maybe I did it as an announcement. Yes. Okay, so this thing, I'll post this as an announcement to my lab sections as well, and then you'll have that. So anyway, you can find some resources for that. Okay. Anything not covered there? Any questions remaining about the lab exercise? Yeah. What you got? If you had lab today, officially the exercise is due today, or Monday, but we'll be forgiving about the deadline. So, try to get it done faster, but don't panic. Okay. But I would rather leave the deadline as is and say, try to get it done on time than it's due. Lab exercises are conventionally due at the end of the day when the lab exercise happens. If it's holiday rules like Monday, it's due the next day of classes. Okay, so you don't have to finish it by the end of the lab session, like ever. Because I know sometimes things go wrong there. All right. Cool. Okay. So that's lab section stuff. Like I said, I'll copy that announcement and share it out with the other sections. I didn't want to overload people with announcements, though. Actually, let me do this. I'll post it through the lecture. Okay, that's fine. I'll do it here. I'll do it through us. I'm helping out a couple of other instructors, so I got their things too. Where'd my stuff go? Lecture. There we are. Okay. Hmm. Well, let's do it there. There we go. Because that's really what it's about. It's about support. So there's TA office hours. Let's see. Schedule throughout the week. There we go. Okay. Cool. Well, there we go. Alrighty. So now I sent that out to everybody. Okay. So let's talk about this lecture stuff then. I got a couple topics to do today. We'll get back to Haystack. All right. So where we left off, we talked about caching. And where I'm going to skip over a couple of these things because they're kind of boring. Maybe I'll come back to them. They in a sense they get repeated later in the lecture anyway. But what I want to talk about in general is Haystack. Okay, so with Haystack, Facebook had this problem. I'm going to lift this so I can blow it up and edit it a little bit. Okay. Hey, you can actually see that really well. Okay. So Facebook had an early problem. Had an early problem that data was often requested in a way that required outside services, right? So photos are big, require a lot of network bandwidth, and Facebook contracted with outside what are called content delivery services providers for that work. Okay. But it was expensive, right? Because those guys don't work cheap. Now, the basic problem Facebook had over here, you can see about half of photo requests, right? Photo views are for photos posted in the last few days. Okay. And conceivably, Facebook could cache just those. Okay, they could do that in RAM and get by. Problem is, though, up here, this is what's called a cumulative distribution. This shows what percent of photos are so old, right? So I'm going to circle with a dot here. This is about, this dot is about, let's say 85% and 365 days, meaning
Send word to your son.
15%.
The Ironborn who surrender will be allowed to return safely to their homes.
All right, I'm going to pause that.
Virtue, your grace, too much.
The Ironborn, with the exception of Theon Greyjoy.
Interesting. Okay. So about 15% of requests are for photos that, yeah, this is the issue with remote learning, isn't it? People might be watching Game of Thrones instead of listening to the lecture. This is why I have people come in. Okay. Down is about 85%, 365 days, meaning about 15% of requests are photos that are a year or year old or even older. Okay. So Facebook has this problem that basically they would kind of have to cache everything. They can't just cache stuff from the last few days. they need to cache literally a year or more worth, right? If they want to get like some target, like 95% of hits in the cache, they need to hold like 3 years worth of photos. And that's just too expensive to do in RAM, right? I mean, technically it's feasible, but it's expensive and they don't want to do it that way. So what do? Well, this is the interesting part, right? Basically, they have to rearrange how their data gets stored. And the short version of that, let me walk you through the process of how Haystack used, or what was there before Haystack. So suppose a user logs into, or, launches Facebook, and Facebook has to immediately construct that user's feed. Okay. So that involves pulling a bunch of photos and other content, from all that users, friends, and other data sources, right? Like ads. Okay. So you launch feed, Facebook goes through, looks through its database and say, hey, let's figure out what stuff we're going to pull to put in this person's feed. Okay. That takes some work, right? So each individual photo pull involves the following checks, right? First of all, find the photo itself. Second, find whether the user has, rights to view it, right? Whether it's public, whether it's visible to it or not. And then, right, so find the photo itself. And then finally, download the photo and, inject it into the feed. Okay. Each of those involves doing a separate disk lookup. Each of those tasks involves a separate disk lookup, which, in 2009 adds a fair amount of time to the loading process. Okay. So what Facebook did as a solution, they rearranged how the data
get like a stress headache, so I'm gonna try and relax because when I get super stressed out.
Thank you. They rearranged how the data was stored and managed. Stored and retrieved. Let's go with retrieved. And the way that works is simply each photo contains not only the image itself, but also the metadata, like who posted it and what visibility it had. Okay, so looking up each of those things previously entailed a whole separate disk lookup operation, which took some time. So instead of that, Facebook said, hey, the metadata is really small, right, relative to the photo. So we can just store all the metadata in RAM. And we can design the photo ID itself to contain information about where the photo is stored and who can see it. So what happens, instead of having to do separate lookups, like, oh, I'm going to get this photo. Well, where is it stored in the system? Okay, great, I found it. Now can I see if somebody can view it? Great. And now if somebody can view it, I need to see if, I need to actually take the time to download the entire photo. So instead of that, instead of each doing a separate disk lookup for each of these, Now we separate the metadata from the photo. We store them in separate systems. The metadata is compact. We can pack it all into RAM. And instead of having to do separate lookups, we say, I'm going to find out whatever the identifier is for this photo, its URL, and its URL structure will in fact contain information about where to find the photo and who can see it. So I can skip those disk lookups entirely. Okay, so short version, pretty much overnight, this tripled Facebook's photo delivery capacity because RAM is so much faster than disk, but the speed increase didn't require any additional substantial hardware expenses, right? They didn't have to buy a lot more equipment or use upspeeded equipment to make this work. They just rearranged their data in a better way. And overnight, they tripled their delivery capacity. And this was really important for Facebook because this reduced their reliance on expensive content delivery services, right? And provided a lot of extra capacity going forward, right? If they'd gone with their old system, it would have been a big problem, but they didn't. So number one, right off the bat, they need to use a lot less of that expensive service for content delivery. And number two, even though people are loading in lots and lots more photos, the cost of adding in those photos becomes cheaper than it had been. Okay, so that's pretty much the story of Haystack. Now it's here in the slides. All right, I talk about some of these things. That's all this stuff, right? But you got the story instead of the slides. If you're interested in reading a little bit more detail, a little bit more formality, the one I would recommend as the most readable to start with is this one. It's a conference paper where Facebook talked about their problem. Check out that, but there's some other news articles about it and some other, more technical stuff. But that first one is probably the easiest to get through. Okay. Anyway, so key takeaway of all that is that the way you store data matters. It can mean, the difference between having a very big system with manageable cost or having your costs run off the rails. So if they hadn't figured out that solution, Facebook might not still be around. They might have gone out of business or, been pushed off to the wayside by somebody else. Okay. Now, the rest of this is all just about basic database management system stuff. All right, so databases are essentially a store of data. So all the things we might want to track. So in this context, we'll be talking about the photo systems, right? So Facebook has not only the set of photos that people have uploaded, but also information about who has uploaded them, when they were uploaded, other metadata about the photo, like maybe where and when the photo was taken, and who can see it in terms of visibility. So all that kind of stuff. Database management system, or DBMS, that's basically the software side of getting that, of how that data is managed and delivered to users. And there's two main flavors of databases. Number one is relational, which most of this course is what we'll be talking about. This is basically the plain vanilla version of databases. And the other is NoSQL. NoSQL is kind of everything else. So we'll start by talking about databases. In the basic relational model, data gets stored in a set of tables, rows, and columns. So we'll go into Paint for that. The basic unit, that's weird. The basic unit of a database is the record. So a record is all the data about a particular thing, like a student or a course or a photo, right? Any particular thing you want to track in your database, a record has all the what are called attributes about that thing that you want to track. So every record contains a variety of, what shall we say, I guess attributes of that thing called fields, right? So for a student, you might have last name, first name, email, UIN, okay? For a course, you might have title and instructor and CRN, right? That's the number, that the 5-digit number they give to courses. And maybe even semester, whatever semester it was being taught. For photo, you might have the photo data itself, the poster, the location, any visibility limitations. Okay, so things like that. Every record is a particular thing, and the record contains what are called fields that have all the attributes about the data that you want to record. Then, typically, records are grouped into tables, right? A table is a long, long list of records. And in plain vanilla relational database systems, every record in a table has the same format. So for example, in a photo table, every photo record would have the same fields, right, given above, right? So photo data itself, poster location, visibility limitations. Their values might be different, but every photo would have those fields, okay? So to flip this around a little bit, a table is a group of same format records. Each record contains a set of fields. Typically, each record within a table holds the same set of fields in the same format. Okay, so this is core database stuff. And for those of you who have already done a little bit of access, you've seen some of this. For those of you that are just getting into it today or later, well, you'll have time, you'll experience all this. Okay, so either way, you're going to get the information twice. Okay. So, for example, the reason why they're called tables, why they're called records, rows, is they basically look like that. So another term for a record is a row, and another term for a field is a column. Because when you write the table out like this, right, you can see that every record is going to be shown horizontally. In this case, the fields are name, email, password, birthday, then ... indicating some extra ones, and then eventually a link to a profile picture, right? And every record has those same things. So each record can also be called a row. Each field, because it has a vertical orientation, often also called a column. Okay. Now, basic database operations, things that you can do with a database, basically you can change data that's there, either change what's already there, or you can add in completely new records, or you can delete what's there. And all of that applies to new records in even new tables. So there has to be a mechanism to create a table in a database, and there has to be a mechanism to create new records. You can also ask the database questions. These are called queries. So a query is something that's used to retrieve data from a database. And queries are especially important because typical databases end up reading a lot more often than they write. So think of an example like an ad on Google. Advertiser uploads the ad once to Google's system, but Google might send it out many, 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 many times to different users on Google. Same thing with Facebook. One person uploads a photo. That photo might be seen by dozens or hundreds of people. Okay, so typical databases end up having to respond to queries as kind of their most important thing. And in a relational database, you can ask queries that span across tables. For example, you might have, just conceptually, you might have one table of customers, well, let's say for Facebook users, and you might have another table for zip codes. Okay. And maybe in the table of users, the fields are last name, first name, we'll say email, and zip code, right? Maybe we include that as a field. And in zip codes, right, you would have the fields zip code and city and perhaps state. So with relationships, what you could do is recognize that this zip code field is essentially the same thing as this zip code field. You do what's called setting up a relationship across those fields in those tables. That'll happen in lab exercise 2. And because you know that they're the same thing, you can use that information to say, hey, if I have a user, right, maybe that user is Smith Fred with email fsmith1 and at uic.edu, and the zip code is 60607. Well, you can look up that same 60607 and recognize that that's in Chicago in the state of Illinois. And so if you want to query on your database, you can look through say you want to ask the question, show me which users, give me a list of users that are in Chicago. You can scan through all the users. For every user, you can find their zip code. You can check it across the table of zip codes here and say, if the city and state corresponding to that zip code is Chicago, Illinois, then you know the user is from Chicago, Illinois. So that's the point of relational databases, is you can set up those kind of connections between tables to answer more complicated questions. Okay. Now, the language for doing all this is what's called SQL. SQL is standard language for anything you want to do with databases. People my age and younger generally pronounce it SQL. There are some people, usually a little bit older than me. I'm right on the cusp. I started out pronouncing it SQL, but then I caved and started pronouncing it SQL. Older people than me often pronounce it SQL. So live and let live. It's unwise to correct people. Don't be that guy. But SQL contains command groups for queries, for all the data manipulation we talked about, like doing adds, deletes, or modifications, changing tables, changing columns, changing their formats, and other things like data control language, which is used to regulate which users can access which data. So SQL has all that. Anything you need to do for relational databases, SQL has a mechanism for, coding that. Okay. Next thing to cover is key fields. So for databases, it's often very important that there's one and only one answer to a query. For example, suppose you ask your database, what is the zip code, or let's do what is the email of the user with last name equals Smith and first name equals Fred. Well, many users might have that first and last name combination, which creates a problem, right? You don't know if you're going to get the right one. So, on the other hand, if we assume that UIC uniquely assigns email addresses, right, that no two students, right, no two users have the same one, then we could ask the system, give me the first and last name of the user whose email is fsmith at fsmith1 at uic.edu. Okay, so in order to have one single correct answer to a query, it's often important to make sure that there's one and only correct answer to the query. And the way we do that is by saying there's going to be some single field or combination of fields that's going to be unique for any user. In the case of UIC, right, if you have a table of students, it could be the UIN, no two students have the same one. It could be the net ID, same thing, no two students have the same one. It could even be the student's social security number. Although foreign students, I guess, probably do not have an American social security number. That's probably, not appropriate. Anyway, but as long as there's a single primary, what's called a single field or group of fields that are going to be unique for every record in a table, you can call that what's called the primary key. And if you look a record up by the primary key, it's always going to be unique, right? No two records in a table are going to have the same one. Okay, so a key field or a primary key field is never duplicated within a table. We'll mostly keep it simple and say there's only one primary key field in a table. A lot of what they do in Access is what's called an auto number, where the first record you create gets a key auto number value of 1, the next one gets an auto number of 2, and so on. So you use that as a key. And generally speaking, your system should automatically check for uniqueness anytime you modify a record. So for example, if a student somehow is able to change their email address, their net ID at UIC, you would want the system to check and make sure that they haven't chosen one that already exists somewhere else in that table, because that would create a big problem. Okay. You can also have records in a table that reference a key field from a second table. In that case, it's called a foreign key. Okay, so in this case, let's see, do it in green. Well, I was trying to do it in green. Let's do it in orange. Here, zip code is a primary key for the zip codes table. Okay, no two records have the same zip code. However, zip code here, zip code in the users table, is not a primary key because many users could have the same zip code value. Okay, so still we use it here, right? So this, for users, zip code is a foreign key, right? A key field from another table. That's what a foreign key is. And so again, if we're trying to uniquely look something up in another table, essentially, if we ask this question, hey, show me all the users from Chicago, Illinois, essentially zip code is our key to get that information. And we know that it'll work as a unique check because it's a foreign key. It's a key field in this other table. So when we say, hey, what's the city for 60607? We know we're only going to get one answer to that. Okay. So in general, with databases, you try to set things up so for any question you're going to ask it, there's going to be exactly one answer and it'll be the correct one, right? You don't want to get multiple answers and you're not sure which is the correct one. All right. Some other concepts related to this: atomicity. So atomicity just means you can't break things apart. So that was the original idea behind the concept of atoms, is they were little chunks of matter that they were so small you couldn't divide them at all. Turned out to be not true, but that's still why they call them that. Okay, sure. A foreign key is a field used by one table that is actually a primary key in another table. Okay, so the users table uses a zip code value, which is not a primary key. But the zip codes dot zip code, right? The zip code field in the zip codes table is a primary key for, the zip codes table. So for users, zip code is a foreign key. Does that make sense? Cool. Yeah, no worries. Welcome. Okay. So with atomicity, what you want to do is create the field in a way that it only has one thing in it, right? So the technical term for what you're trying to avoid there is what are called multi-valued fields or attributes. So an example for this, suppose you had a phone number field, and the phone number field didn't just get one phone number. You could put in a list of phone numbers. Well, when you ask the system, hey, give me Joe's phone number, you're not going to get just one single number. You're going to get a list of phone numbers. And depending on what kind of number you're trying to get, that may be helpful or it may just be confusing. So if you need to store multiple phone numbers in your system, like home phone, work phone, daytime, nighttime, cell phone, landline, whatever, okay, you would want to all have those as separate fields in the table so that you say, hey, I need Joe's cell phone or I need his work phone. You know exactly where to go and where that's going to be. Typical relational database models assume all fields are atomic. Most databases, this is what happens. Fields are designed to be atomic. And again, all that goes down to the idea that anything that exists in one place, you know exactly where to look for it. It's only going to be in one place. And it also makes it easier to manage uniform data formats, right? So for example, if the phone number field was just, an unbounded, say you could put up to 1,000 characters of text in there. Yeah, you could put a lot of phone numbers in there and you could put some descriptive text, but in your automated system, when you ran that query, you'd get like this list of phone numbers. Maybe it would show you all those and the user would have to figure out which ones are which. But imagine if you're trying to run a query to just pull all the cell phone numbers of all users or all work phones of all users. You'd have to write some additional code to extract that data and look for the words work and then format it afterward. And then there'd be no real way to check. There would be no simple way to check and make sure that the phone numbers you put in there in the first place had the correct format, because you could just have 1,000 characters of pretty much anything as text there. If you say this field is only going to contain one phone number, you can force it to be just a 10-digit string. And if it's not a 10-digit string, then the system doesn't accept it in the first place. Okay. Other stuff, metadata. Metadata we've talked about is just data about the data. So metadata includes things like names of tables and columns, basically any labels you might put on the data. That's going to be metadata. The type of data in a column. For example, if you have integers or floating point numbers with decimal points, or if you have the data written as a time or a date or just unformatted text, right? That's metadata. It doesn't affect what's stored in the database. It just describes how it's stored. And any other formatting issues like maximum values, minimum values, maximum length, number of decimal places, stuff like that. So basic ordinary relational database design practice, and this is what Access enforces. Within a table, every record has the same format. So all of the columns of a record also have the same format. So for example, you might say enforce last name might be limited to 20 characters. First name might be limited to 12 characters. Email might be limited to, I don't know, 20 cares. You know, and it might have to include the @ symbol, and it might have to include a, you know, a dot afterward, things like that. Zip code might be enforced as 5 or 9 digits, depending. Okay, but every record in that table would have the same format for that field. Okay, we'll come back to that in a little bit, but that's your standard relational database format. And again, Access enforces that. When you specify how a field is going to be formatted for a table, that formatting is going to be applied to every record in that table. Now, one of the things that can go really, really wrong is when data sizes are wildly divergent, like images or videos. Okay, so you can have the case where some images are very big and have high resolution, others are small and black and white, require hardly any data at all. So this is one of the basic database problems we'll talk about in a minute. Okay. I'm gonna skip this. I'll maybe come back to it in a minute. So talk about this where relational databases make sense. The reason why we have this common format, the reason why vanilla relational database systems use standard formats throughout a table is that it makes data easier to locate. Okay, so for example, suppose a customer record consists of exactly 100 bytes of data. Okay, so maybe it's 32 for the last name and 30 for the first name and 38 for the email. Okay, I'm just doing that to keep numbers simple. Then, if record 1 starts at memory address 1, right? However this is done, then record 2 starts at memory address 1 plus 100 equals 101. And record 3 starts at 101 plus 100 equals 201, and so on. It's easy to locate things. Likewise, if you just need to find the email, you know the offset is the start plus the offset is 62, right? So if record 1 starts at memory address 1, then for record 1, email is at address 63. And record 2's email is at address 163. And record 3's email is at address 263. Okay, so this formatting makes it very easy to look things up. Standard formatting for all fields, records in a table makes it easier and faster to look up data, right? You don't need to check every byte of a record. You just need to check particular memory locations. Okay, it's a lot faster. That's why the standard formatting is important. Okay, so, but this means if you're doing this, then the problem becomes, all right, now let's consider the case of a big photo. All right, so suppose this. Suppose your system stores photos. And most photos are about 1 megabyte in size. But some are as big as 20 megabytes in size. Okay, well, with the regular standard field format approach, each record has to allow for a 20 megabyte photo. Okay, but that means something like 95% of the memory storage capacity will be wasted, right? Even though each photo could be 20 megabytes, most are only about 1 megabyte. So the storage capacity is wasted. This is a problem. Okay, this is why if you have data types with wildly divergent sizes, it becomes a big problem, because Facebook, for example, they have a lot of photos, they're divergent sizes. YouTube, they have a lot of videos, and the videos are of divergent sizes. Although, as we'll see, they adopt a different approach. We'll talk about that around the end of the course. Okay, so on the other hand, with text, the costs of size variations are pretty small, right? So suppose like Facebook has a few billion users and their account info has maybe, well, I don't know, let's say 1 kilobyte of data, then they need a few terabytes of data storage capacity, right? Which is and isn't a lot, right? But for Facebook, the costs of RAM would be manageable. And even for us, right, for ordinary people like you and me, we could get a 4 terabyte hard drive. I haven't priced one out for a while, but I'm going to guess probably for a few $100s at most. Okay, so with text, even though the same problems tend to arise, the fact that the volume of data you're dealing with is a lot smaller means there's less concern about it. When you're talking about videos and the aggregate amounts of data go up into the exabytes, well, 95% of 20 exabytes is a lot of money. 95% of a few terabytes is not very much money. Okay, so because of this problem and others, sometimes businesses want to get away from the vanilla database model, right? And that family of solutions is the NoSQL model, right? NoSQL stands for not only SQL, right? So to an extent, they might be compatible with relational databases, but basically they cut some corners. There's some things you give away to get something a little bit different back. Okay. So let's go back and skip those. So with relational databases, suppose you have a very, very big one set up. Okay, we'll talk about this. Suppose you have a very big database with exabytes of photos, okay? If you wanted to change the format of that database, you'd have to rewrite and move around a lot of data, right? Especially considering that some data, like popular photos, are stored on different media or different locations easier to read. Okay, so changing it is a big hassle. Number two, any system-wide queries might have to look at many pieces of hardware simultaneously and joined by network connections instead of just scanning one bank of RAM. So if you're trying to do something on one machine and all of the stuff you're working with is in RAM, it's probably going to be fast. But if you're trying to do a query using some standard off-the-shelf software, what'll happen is they'll read one batch from one machine, access where that data is stored on disk on another machine, load it, combine them together, do whatever processing they need to do, run that part of the query, then get the second chunk from that next machine reading it from disk, right? It's going to go really slow. Even best case, even if it's stored in RAM on two separate machines, it's still going to need network time to bring those together. So anytime data is stored on multiple machines, the regular relational model might need some modification, right, to work at scale. You're going to have to do things a little bit differently. One of the things we talk about that. So here's in the cons. So relational database model, it's not flexible once the system gets big. If you're doing something little in accessed, with like a few hundred or a few thousand records, sure, you go ahead and you change the format in there and it's not a big deal. But if you're talking a system that's Facebook size, that's already been pretty well optimized to, deliver data quickly, if you're going to change the formats of data stored on those machines, it's going to be a lot of work to make things work well. Second, sometimes the data you're gathering doesn't neatly fit whatever table setup you have. So schema is basically a fancy word for design. So you might have some design in mind for how your database is going to be set up, but maybe you're pulling data that's jointly created by two applications, like a security application and some ordinary application. And the security application extracts certain data from the other application. Well, you get some combination that might be unique for that particular combination of applications and even the time where they're running. And it's hard to put all that in one table. And finally, relational databases, the way they work, they say here designed to run on single servers. It's just if all the data that you're working with is stored in RAM in one place, it's going to be pretty fast. If you start having to do network communications to share data back and forth, well, that's going to be, orders of magnitude slower. So relational data, this basic model tends to work pretty well if you have a stable table on a single machine and it's not too big. Any of those things goes away, it becomes a big problem. So there's a bunch of different NoSQL systems out there. Some of you might have heard of MongoDB for document storage or Dynamo for Amazon's cloud. Cassandra was one that Facebook developed for doing sharing instant message data, storing that. You also have problems like this. For example, if you have a big problem that involves extracting data from a bunch of different machines at the same time, one of the things you can do with that conceptually is you have a big problem, right? So some big problem, like a query that has to run on a very large database table, possibly stored on dozens or hundreds of separate disks. Okay, so the information is there, it's in the database, but it's not really feasible to download chunks of data from one machine, bring them over to another, analyze that data, and add stuff to it. Instead, what happens is the query gets sent to all those many different machines, and it runs in part on each of them, right? So together, each machine has a part of the problem, right? So the query is broken into segments, and each segment is processed on a separate machine. Okay. And then eventually, at the end, they're all going to be recombined. I know I'm drawing the arrows here. One more. So each of these machines does its part of the work separately, and at the end, they all combine their results back together. Well, that's an arrow there. I just did it all as one. And brings all the results together, right? So all the matching query results are combined in one batch. So your problem might be, find all users who are friends of Doug who have posted a photo in the last week, right? So, and all that information is going to be stored on a bunch of different machines somewhere. So that query gets sent to, hey, in this section of the database, find those users here, find those users here, find those users, right? And at the end, maybe, they look up and say, okay, here's a few that I found. I'm trying to grab that rectangle. Here's a few, and 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 here's a few. And it combines all of those different sections together to get one complete result at the end. Now, this is something, you're not going to do this with your basic off-the-shelf copy of Access, right? It requires a new and special system that can handle this. So one system that was commonly used for this kind of problem was called Hadoop. Hadoop was like the biggest thing since sliced bread about 10 years ago. Google used it, other operations used it. Since ones that are more concerned about speed, they've switched to something called Spark. Spark is basically the same thing as Hadoop, but instead of working on disk, it works on RAM. So more expensive, but you get faster results. Okay, so I think this is a good break point for people who are winding down here. I just want to mention one last thing before we go. So in terms of delivering data, I'll just do these couple slides and we'll call it a day. Facebook has to have a lot of data all around the world, right? So they have different data centers worldwide, and all of them might contain some of the same data, depending on what's going on. For example, if I make a post, it's immediately going to get sent to the data center near to me. But if I have, friends on the other side of the world who are like interested in content that I'm posting, then it might, get stored over there for a while too. Now, the reason with this kind of situation, why do they do it this way, right? Why does Facebook distribute data all around the world instead of just keeping it in one place? Well, if they kept it all in one place, number one, single biggest thing probably is that it's going to be slower response for a lot of users. If the users are far away from the hardware where the data is actually stored, it's going to take longer to deliver that data to them because the electrons don't teleport. They, have to travel over some sort of wires, or their photons traveling over cables, but they still get checked as electrons at some point. Okay. Other thing, potentially brittle reaction to failures, right? If that one big data center goes down for whatever reason, there's an earthquake, there's a human-created disaster or whatever, that could be a huge problem. With data centers all around the world, it's a lot less likely that a problem like that happens. So typically the way these kind of systems are set up is they have multiple copies of data, get stored at separate server groups worldwide. If they need to, right? If some request comes in and the data center doesn't have the data that's locally, doesn't locally have the data that's been requested, they can forward that request to other data centers that they know have it. And the importance of this is, number one, less latency, data gets delivered faster, the system's more reliable. If there's a failure, it only affects that one. There's some other issues too about caching. Mm, we'll come back. We'll come back and talk about that. I think this is a good break point for now. We'll come back on Thursday and I'll open up with talking about churn a little bit more. How how time zones affect these kind of issues. Okay, so this is it for lecture today. I posted the announcement about the lab exercise. Is there anything else I needed? Can't think of it. All right. Any questions? Any more questions about any of this stuff? Happy to talk about it a bit, but if not, we'll come back. We'll talk about it on Thursday. We'll talk about more about decentralization. It's better to talk about some of these things in person when when we're all together in the same room. All right. Nah, no iClicker today. It's kind of early in the semester anyway, so usually attendance is good, morale is good, so not worried about it at this point. All right. So that's all I got for you. It's been a hoot. I hope you learned stuff. And we'll come back on Thursday. We'll talk about things. All right. All right. Yep. Thanks. You too. We'll see you next time. All right. Bye-bye. Yep. No worries. Later. I'm out.